Hello and welcome to today's webinar presented by Dlubal Software. Today we'll be working in our finite element analysis and design software, RFEM. The topic for today's webinar is nonlinear time history analysis in RFEM. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the U.S. office and also a technical support and sales engineer, and we are located in Philadelphia, Pennsylvania. My colleague Stefan Frenzel will be your moderator, answering any questions you may have. He's a product and customer support engineer located in our Leipzig, Germany office. If the control panel does seem to get in your way when you logged into this GoToWebinar, feel free to show or hide that with the orange arrow up at the top. We always want to encourage everyone to ask questions throughout the webinar. You can do so within this same dialog box. If by chance I don't get to all your questions, I will certainly send you a follow-up email afterwards. So to quickly go over the content for the next hour today, I want to go over the overview and features of the RF-DYNAM Pro modules. And in particular, we'll be focusing on both the linear and nonlinear time history analysis within these dynamic modules. And finally, we'll move on to an example within RFEM. This will be machine-induced vibrations on a steel structure. We'll go ahead and perform a natural frequency analysis. And with this, we'll have two different cases. In our structure today, we're going to have tension-only members. Now, the natural frequency analysis is a linear analysis. So by default, the program will automatically substitute in a truss member for those tension-only members. The second case that we want to take a look at is how our frequencies and mode shapes change when we actually deactivate those failing tension-only members. We will take a look at a linear time history analysis, and in particular resonance. Resonance is where the excitation frequency coincides with the natural frequency of our structure. And finally, we've recently added nonlinear time history analysis in RFEM. So with this, we'll take a look at a couple different nonlinearities that we can now account for, such as tension-only members, as well as a failing support. So regarding the dynamic add-on modules in RFEM, RFEM is our main program. This is where we're going to fully model the structure. We can load it with some various static loading and run an analysis. But anything to do with dynamics, whether that's a natural vibration, force vibrations, or seismic analysis, does require one of our dynamic add-on modules. So the first is RF-DYNAM Pro Natural Vibration. So this is going to run an eigenvalue analysis that allows us to find the natural frequency and mode shapes of our structure. Now this is a prerequisite in order to run any of the additional add-on modules that we have for dynamic analysis. The second is RF-DYNAM Pro Force Vibrations. Now this allows us to run a linear time history analysis, which is what we'll be taking a look at today. We can also run a multimodal multi-point response spectrum analysis. We won't be touching on this point today, however. So below you can see a chart, which is a time course monitor of a tension-only member. Now this is showing the axial forces within this tension-only member. Now because this is a linear time history analysis, as I mentioned before, similar to natural vibrations, we will simply replace the tension-only member with a truss element. The truss element can take both tension and compression. So as we're looking at these normal forces over the allotted period of time for our time history analysis, we'll see tension forces, but then we also see compression forces here, and that's just simply a limitation of a linear analysis. Now, we've recently added RF-DYNAM Pro Nonlinear Time History. So this is a module extension. You do have to have DYNAM Pro Force Vibrations in order to add on this module extension, which provides nonlinear time history analysis. So now if we take a look at that exact same type course monitor for the same member, tension-only member, we now see a little bit of a difference here. We only see tension forces within that member. So what happens is when we have any type of compression within the member, it completely fails. And yet when we reintroduce tension forces within the same member, the member is reactivated, and so on throughout the entire course of the time analysis. The last module that we have is RF-DYNAM Pro equivalent loads. This is a multimodal response spectrum analysis with the generation of equivalent static forces. Now, I did an entire webinar focused on only this module, so I would refer you to our YouTube channel if you're more interested to see this, as we won't have time to get into it today. So now looking at RF-DYNAM Pro natural vibrations in a little bit more detail. Again, this is an eigenvalue analysis that allows us to view the frequency and mode shapes of our structure. We can directly import masses from load cases, load combinations from RFEM, or we can manually apply masses within the module itself, and eventually we want to create mass combinations. We do have the diagonal consistent or unit mass matrix available here. And again, this is a linear analysis. So something like a tension-only member is replaced with a truss member. Now there's some other nonlinearities that may be simply ignored as well, such as a failing support. However, we can import initial conditions such as stiffness modifications, axial forces, failing or deactivated members. And that's actually what we'll be taking a look at today. We'll import in the failed tension members of our structure to see how the frequency and mode shapes change due to those deactivations. So as I mentioned before, with time history analysis, we have both the linear and nonlinear options available. Now, as far as the linear time history analysis, this is available in Dynam Pro Force Vibrations. We have two different solvers, the modal analysis solver and the implicit Newmark solver. Now, I'll get much more into detail on these solvers in just a minute, but as an overview, the linear analysis neglects structural and geometric nonlinearities. This does run a first order analysis and assumes small deformations. Now, again, nonlinearities in the model are replaced, as I've already mentioned, with tension-only members, but also with compression-only members, with cables. They're all replaced by truss members. And by the way, a truss member in RFEM is nothing more than a typical beam element that can take both tension and compression. And all we've done is release the moment and releases. Now, other nonlinearities may be completely ignored, such as support conditions. As far as the nonlinear analysis, this is available with the module extension RF-DYNAM Pro Nonlinear Time History. So there are two solvers available here as well, the explicit solver and the implicit Newmark solver. In RFEM, this is going to assume large deformation analysis, and all nonlinearities that are defined within the model that we define within RFEM can be considered within the time history analysis. Now, for both of these solvers, whether linear or nonlinear, we have two different options. We have either time diagrams or accelegrams. So with time diagrams, this is a force or moment excitation at an arbitrary position. We define our time diagrams with tabulated values, which can be imported in directly from Microsoft Excel, for example. It can be a periodic function, or it can be a direct input of a function within the edit field. Load cases define the location and the excitation of how this load will be applied according to the time diagram. So for example, we would apply loads within these load cases, nodal loads, member loads, surface loads, and many other options to determine where exactly this excitation will take place. The combination of several independent excitations is possible, and the excitation can also vary over time and position. Now, as far as accelegrams, well, this can be taken into consideration with time diagrams that can be imported in from a library of earthquake recordings, which we have available directly within the module, or it can be user-defined. Now, the difference here is that this is an excitation at the supports. A multi-point option is available as well for the linear analysis only. Now, regardless if you're running a time diagram or an accelerogram, the display of results are both available on a time course monitor, and this is certainly something that we'll be taking a look at quite a bit today. We can export the results into load cases for single time steps, so you can actually see the response of your structure at each individual time step back in RFEM, or we can export out a result combination for the result envelope. So to give you a little bit more detail on the solvers, we'll begin with the first linear solver, which is the modal analysis. This is a decoupled system based on the natural vibration case. Therefore, a certain number of eigenvalues are required to ensure accuracy. So if you determine to this natural vibration case, if you set the eigenvalues to something that's far too low, then your results are not going to be accurate when it comes to the time history analysis utilizing the modal analysis solver. This is a multi-degree of freedom system transformed into many single degree of freedom systems. And we have some more information on this in our manual and in our literature and some verification problems available on our website if you're more interested to see exactly how this works. The mass matrix and stiffness modification are taken directly from the natural vibration case. Now we can consider structural damping, and in particular Lear's damping. Lear's damping, as engineers, we're probably most familiar with this. This is just a damping ratio that we'd like to achieve for our structure. Now you can set different Lear's damping values for the different eigenvalues from the natural vibration case. And unlike any of the other solvers that we'll be taking a look at today, you also can define an initial deformation. The second linear solver is the implicit Newmark solver. This is a direct time step integration. Therefore, eigenvalues are not even required. There's absolutely no assignment of the natural vibration case. You don't even have to run a natural vibration analysis in order to move forward with this particular solver. In turn, that means that the time step is now incredibly important for the accuracy of the results. If you set a time step that is much too large, then your results from this linear analysis will be incorrect. Now, there is a fine line. If you're setting a time step that's really, really small, well, that's going to take quite a while to solve within the program, when in reality, your results might not change much if you were to set something slightly larger. So we do have some recommendations as far as a time step within the program. And you can see that listed here. Delta T is less than or equal to 1/20 times the frequency. Now, the frequency in this equation is the largest frequency from either the natural vibration of the structure or of the excitation frequency. Both the diagonal and consistent mass matrix are available here, and stiffness modifications or initial deformations cannot be considered. We can also consider structural damping though. However, this is in reference to the Rayleigh coefficients with alpha and beta. So we need to somehow convert Lear's damping into the Rayleigh coefficients, which we'll be taking a look at today with our example. So now moving on to nonlinear time history analysis. Again, this is something new that we just recently added. And now we have the ability to define two different solvers to utilize, either the explicit analysis or nonlinear implicit Newmark analysis. Well, with either one of these solvers, nonlinearities within RFEM are now considered. So the question might be, well, what exactly are these nonlinearities that we can consider from RFEM? Well, here is a nice screenshot showing you the global settings within RFEM where you can activate or deactivate some of those nonlinearities. So as I already mentioned, the member type, tension only, compression only cables, but we also have support nonlinearities. We have member end releases that we can define nonlinearities such as tearing, yielding, friction, things like that. We also have contact solids and member material nonlinearity. So a plastic analysis for steel, isotropic thermal elastic material models. This can all now be considered with a time history analysis. So the large strain deformation analysis is assumed here, and the direct time step integration is utilized. Therefore, eigenvalues and natural vibration cases are not considered. So again, we don't even have to run a natural vibration case. However, it's always important to study your structure in order to determine if resonance is going to be an issue. So in our example today, we'll still move forward with a natural vibration case as well. Looking at the first nonlinear solver in a little bit more detail, well, this is an explicit analysis solver. This is best for short duration excitation, such as an impulse, an explosion, or rapidly changing nonlinearities. Now, in order to get a conditionally stable model, your time step, delta t, must be less than or equal to delta t stable. Well, the question is, what is delta T stable? And you can see here that I've actually listed this formula here. Now, the program can automatically determine what delta T stable is. So by all means, you can use the automatic time step within the explicit analysis solver. The equation is 2 over omega max plus the square root involving Lear's damping ratios. Now, remember that I said with either one of these solvers, you do not need a natural vibration case. So without the natural vibration analysis, how do we determine what omega max is? Well, we don't. In practice, delta T stable will be utilized as this equation here, LE over C sub D, where LE is our finite element length, C sub D is the square root of Young's modulus over the density or the dilation wave speed for linear elastic material. So this is how we estimate what delta T stable will be without the natural vibration analysis. Now, the diagonal mass matrix is only available here with the explicit analysis. We can consider structural damping here with Rayleigh coefficients, but the limitation is only the alpha coefficient can be set. The beta is always equal to 0 when we're utilizing an explicit analysis. The second nonlinear solver is nonlinear implicit Newmark analysis. Now, this provides an unconditionally stable model or analysis independent of the time step. So unlike the previous solver, we'll always get a stable analysis. However, the time step determines the accuracy of the results. Again, if you're setting a time step that is much too large, your results are going to be inaccurate. So a time step study convergence should be run to determine, okay, well, as we continue to decrease these time steps, are my results significantly changing? All mass matrix options are available with this solver, and structural damping can be considered with the Rayleigh coefficients with both alpha and beta. Okay, so that is all for the theory to begin with. So let's jump into the model. As you can see here, I went ahead for the sake of time and modeled a steel structure. We have some W8 by 35s for our columns, W8 by 15s for our beams, and you'll notice that I have lateral bracing members here. Well, these are my tension only members. I can double click here and see the member type is set to tension only, and again, we have some other nonlinearities like compression, cable members, and so forth. I have added a few load cases in here. Now, the first load case is dead load. This is just within our main program, RFEM, and this dead load includes self-weight already, and I've applied a couple area loads. Now, I can right-click to display these area loads separately, and what you can see here is I've excluded some of the transverse beams. They're only applied to members in the global X direction based on their tributary area. So just a typical dead load. Now, my second load case is the dead load from my machines. Now, this is some type of industrial structure, and we know that there's going to be a couple machines placed on this structure around where these openings are located. Now, these machines inevitably have a dead load themselves, so we need to apply that weight or that force to the RFEM model within load case 2 here. So all I've done is I've taken the total weight of the machines, the mass, and then I've divided by the total length here around the opening, which is about 33 feet, in order to get a member load for both the top level and the second level. So those are really the only two load cases I want to consider for now for my natural vibration analysis. Now, in reality, we could continue on adding snow loads, live loads, and so forth, but we'll just go ahead and move forward with our two dead loads. So now we want to launch the RF-DYNAM Pro modules. So we can access the Dynam Pro modules in the Project Navigator over here, and you can see here is our very long list of add-on modules. We can also access them with the drop-down box up here at the top under add-on modules. They're categorized a little bit more clear. So launching RF-DYNAM Pro Dynamic Analysis. So as you can see, all 4 of our Dynam modules are all located within this single dialog box. Now, we don't have to worry about remodeling any of our members, our materials, our loads, our support conditions. Everything is taken into this dialog box. All that we're doing is specifying a little bit more input that relates to the dynamic analysis alone. So we can activate or deactivate any one of the modules here. I'm going to leave the natural vibrations activated for now, and I'm also going to activate the mass combination combinations, which brings up an additional tab. Then I just simply work from left to right. So my mass cases. I want to create my first mass case, and we'll call this one dead load of the structure. I want to import the masses, but the first thing I want to do is uncheck the self-weight. If I leave the self-weight checked here, I will account for self-weight twice because I've already accounted for it in my first load case back in RFEM. And instead, I'm going to import in that first load case with the area load and the self-weight already considered. Now, we can manually define additional masses at nodes, lines, members, or surfaces if we had them defined in the model here. So it doesn't necessarily always have to be from a load case or load combination within RFEM. So I can make a copy of this mass case, and this time we can rename it to the dead load of the machines, and we'll import in from our second load case the dead load of the machines, which we can see here in the background in RFEM. So that's all that I want to do for defining my mass cases. So moving on to mass combinations, this is where I'm going to combine my mass cases to create my first mass combination. Now you can create as many combinations here as you'd like. This is nice so that if we want to maybe study how the structure behaves based on one mass combination versus another, where we're deactivating masses or activating other masses, you can do so by creating multiple mass combinations down here at the bottom. The mass case factor can be adjusted here. Right now it's set at 1 or 100% of that mass acting. You can always manually type that in or use the drop down here. So we only want one mass combination for our case today, so we'll continue to move on. Now the natural vibration case. So the first case, remember from the PowerPoint, I said we're going to run two different cases. The first is where these tension only members are going to be replaced by a truss member. So we would like to set the lowest number of eigenvalues to calculate to 10. The scaling and mode shapes will leave this as the default option here. And under the calculation parameters, well, we just created this mass combination, so we certainly want to utilize it. The type of mass matrix, you can see here the diagonal, the consistent, or unit are all available. We'll utilize the diagonal matrix in translation and rotation, so now you can see all 6 degrees of freedom are activated here. The stiffness modifications. So you'll take a look now. We have this set to no stiffness modifications. So remember that for this first case. So our second case, we'll come back and make some adjustments here. But for now, we would like to consider no stiffness modifications. And we're ready to run OK and calculate. So the program will quickly cycle through this. It will dump us back into RFEM. Now, realistically, we're still in this add-on module. You can see it within my drop-down box here, RF-DYNAM Pro. I'm just viewing my dynamic results graphically and within this table back in RFEM. So according to my table here, table number 5, these are my dynamic results. I can see here my natural vibration case is set to the table right now, and I have my 10 different mode shapes. So I can cycle through these mode shapes to view how the structure is behaving based on the different eigenvalue modes. Now, probably the most important table that we immediately want to jump to is the effective modal mass factors. So this is going to show me my mass participation in the global X, Y, and Z directions. This is also going to tell me what my dominant modes are. So if we take a look at mode shape number 1, well, this looks to be the dominant mode shape in the Y direction. I have the most mass participation at 64% here. And moving on down the table, it looks like mode shape number 6 with 86% mass participation in the global X direction would be my other dominant mode. So with those two dominant modes in mind, we're going to jump back to the natural frequencies tab here and to take a look at what the angular frequency and natural frequency are. So according to mode shape number 1, angular frequency 6.4, natural frequency 1.02. We move a little bit further down to mode shape 6. The angular frequency is 25.8. The natural frequency is 4.1. These are two really important numbers that I want you to keep in mind, 25.8 and 4.1. So this is the natural frequency analysis of my structure. And I know that I'm going to be placing these machines on this structure. They're going to be rotating. They're going to be inducing some external excitations onto this structure. And they also will have an angular frequency and frequency within hertz as well that will be applied to the structure. So the question is, do we need to worry about resonance? What is the frequency of these machines? Do they coincide with the frequency of my structure? Am I going to get deflections that ultimately may cause the structure to fail because those two frequencies are so close together? So that probably tells us that we want to run a time history analysis. So here, back to the PowerPoint, let's take a look at some calculations for these machine-induced vibrations. So I was given the information that I have 2 rotating machines at 246 rotations per minute. Now the mass of the machines is 2,000 pounds. Now of that, the mass of the rotors is 700 pounds, operating at an eccentricity of 0.75 inches. Well, in order to find the excitation frequency, all we need to do is to take 246 rotations per minute divided by 60 seconds, and we get 4.1 hertz. The angular frequency is 2 pi times the excitation frequency, which gives us 25.76. Now, remember back to my natural vibration analysis, mode shape 6, we remember frequencies that line up almost identical to these two of our machines. So that immediately tells me, okay, I could have a serious problem here with my structural design in the case of resonance. So moving forward with the time history analysis then, I want to turn these frequencies into a centrifugal force. Now, the force is going to be applied to my structure as a static load because this is what's going to tell the program, okay, this is the location that my excitation is going to take place that I'll eventually apply to my time history analysis. But we first need to convert these frequencies to an actual force. Well, this is done just by taking the angular frequency, squaring it, multiplying by the eccentricity, which was 0.75 inches, times the mass of the rotors, which eventually gives us 0.9 kips. So we have this force here, 0.9 kips, and as this machine is rotating here in this circle, as we can see from this picture, at one point in time, we have 100% of the horizontal force acting on the structure, the 0.9 kips. But as it continues to rotate, at another point in time, we're now going to have 100% of the force acting in a vertical direction. But somewhere in between here, we're going to have some type of relationship between the horizontal force and the vertical force acting together. Well, this gives us a pi over 2 phase shift between the vertical force and the horizontal force that we want to take into consideration for our time history analysis. So jumping back to the model here, we would like to move forward with our time history analysis. And within RFEM, I've already created a couple different load cases. Here is my centrifugal force in the vertical direction. This is a completely empty load case right now. So what I'd like to do is to take that 0.9 kips and apply it in the vertical direction where these machines will be placed and applying the excitation to our structure. We'll do this with a new member load. So the member load, what I'm going to do is I'm going to take the 0.9 kips, divide by the total length here of my opening, which is about 33 feet, to give me my magnitude of negative 0.028 kips per foot. And I want to apply it in the global Z direction. I click OK. I can zoom in here and just simply click on the members where those machines will be placed, and I have my first vertical load applied. Now I want to do the exact same thing down here on my lower level. I just simply click at the locations where the second machine will be placed, and I have my second vertical load. So again, we created this fourth load case, the centrifugal force, in the horizontal direction. Exact same concept here. I apply a new member load. I keep the magnitude the same. The only thing I want to change is the load direction in the global X. I click OK. I zoom in here to where my opening occurs. I click on my members to now create that centrifugal force in the horizontal direction only. I do the same thing on the bottom level to every member that's applied to that opening. Okay. So now I just have these basic static loads within RFEM. That's all I've done here, but we actually need to provide some type of time diagrams to tell the program how this force is going to vary over time. With this, we'll launch the RF-DYNAM Pro module again. So here we can now activate RF-DYNAM Pro force vibrations for a linear time history analysis according to a time diagram. So now you can see I have a couple different tabs available up here at the top. So taking a look at our time diagrams, we want to create the first time diagram description, and this will be vertical component. And as I mentioned in the PowerPoint, we can import in transient information from Microsoft Excel, for example. We can enter in a periodic function, which we'll be utilizing today, or you can type in a direct function here. As far as the periodic function, remember from the PowerPoint, we already solved for what the angular frequency of our machine is. This is going to be 25.76. The shift is going to be 0. The multiplier is going to be 1.0. Now the multiplier is 1.0 because I've already defined the correct magnitude for my machines back in the load cases within RFEM. So now I can see here my sine function displayed along my diagram according to these values that I entered in here. Now I'm going to make a copy of the vertical component, and instead we're going to call this one horizontal component. Everything remains the same here. The only thing that we'd like to adjust is the shift. Remember, we have a pi over 2 phase shift. In radians, that's 1.57. So now we have a cosine function. So at time equals 0, this is where we're going to have 100% of that horizontal load acting on the structure. But then we move a little bit later on in time, and about 0.06 seconds, we have 0% of that horizontal force acting. Now, that's in turn to the vertical component. We have 0% at time 0, and at time 0.06 is 100% of the vertical force acting. Now, in between this region, well, we're going to have some type of relationship where both forces are acting together. Under the dynamic load case, so our first load case description here is going to be linear time history. And as I have mentioned in detail within the PowerPoint, we have two different solvers here for a linear analysis: linear modal analysis, linear implicit Newmark analysis. We're going to move forward with the Newmark analysis today. As you can see, I cannot select a natural vibration case. This is grayed out. That's because a natural vibration case is not required. It's not considered for this type of solver. That's opposed to the linear modal analysis, where we would consider one of our natural vibration cases. The time history analysis, well, this is where we need to relate these static loads back in RFEM to our time diagrams, our sine and cosine functions that we just created. So what we're going to do is to utilize load case 3 back in RFEM, our centrifugal force in the vertical direction, and that's going to be related to my vertical component. It's as easy as that. Now we want to do the same thing for the horizontal centrifugal force. Remember that load case 4, which is the one we're displaying here back in RFEM, and we're going to relate it to the time diagram for the horizontal component. Time steps and maximum time. So the saved time steps here, well, this is just going to be utilized for a couple different things. Number one, it does not matter for the analysis. What this is important for is for viewing our results back in RFEM. You can export a single saved time step or multiple saved time steps as load cases back in RFEM if we wanted to. So that is why this value is important here, as well as something like the time course monitor. Well, we want to have a nice smooth time course monitor, so I might set this at something like 0.01 seconds. The maximum time is what I'm going to consider for this full time history analysis at 10 seconds. Now here's a time steps for calculation, and this is a part that's really, really important. Now for a linear Newmark solver, I do not suggest using the automatic feature. There are additional solvers when we get into the nonlinear analysis, as I mentioned, that the automatic is fine to use. But for the Newmark, you manually most likely need to set this. That's just simply because the automatic solver will set something too large just based on the functions I've entered in for my time diagram. So way back in the PowerPoint, I had mentioned a suggestion of a time step equal to or less than 1/20 times our frequency. Now remember, the frequency is the largest frequency from either the excitation or my natural vibration analysis. In our case, this was exactly the same at around 25.8. So this comes out to about 0.001 seconds. We can create a result combination here, as I mentioned, so this will just give us an envelope solution for all of our time steps considered. The calculation parameters. Here is where we want to activate the mass combination that we previously created. And the mass matrix, again, we have both diagonal and consistent available here. We'll utilize the diagonal matrix for translation and rotation. And finally, damping consideration. So as I mentioned with this solver, Lyra's damping cannot be considered. Instead, we have to convert that to Rayleigh damping. So as I mentioned, us as engineers, we're probably most familiar with Lyra's damping and those damping ratios. For example, today's structure, I'd like to set the damping at 1% for the steel structure. Concrete might be something more like 5%. So the question is, how do we convert this Lyra's damping that we're also familiar with into Rayleigh damping? Well, it's actually quite simple. The first thing that we want to do is consider the dominant frequencies of the structure according to a linear natural vibration analysis. And as we recall, that is mode shape 1 and mode shape 6. So we can see here the frequencies considered in the global Y and X directions for these two dominant mode shapes. And to convert from Lyra's damping to Rayleigh coefficients, it's just a simple equation. On the left-hand side is our Lyra's damping, so that would be my 1%. On the right-hand side, we have our alpha and beta coefficients, and we have omega for that dominant mode. So therefore, we have two equations, two unknowns, and we can easily solve for what alpha and beta are equal to. So this is what I came up with for our structure today. Now, I do want to point out this graph here in a little bit more detail because I find it somewhat interesting. So this graph is actually what you'll find in a lot of literature that goes into detail about dynamic analysis and damping considerations. And this is actually our Rayleigh damping plotted on a graph here for our structure today. So Lyra's damping is on the vertical axis. On the horizontal axis, we have the angular frequency. Now, the green line here is Rayleigh damping. It's this actual formula plotted out here with my alpha and beta values that I solved for today. Now, the whole point or the nature of Rayleigh damping is to show you that damping is different for each frequency. So that's why we have somewhat of a curve here for our Rayleigh damping. Now, there are several other lines here on this graph. Well, the dotted lines indicate my dominant mode shape. So here is my mode shape number 1, the dark green line mode. We can see omega 1 here. And then the orange dotted line is omega 6, my dominant mode shape 6. Well, I've adjusted alpha and beta so that if we follow these dotted lines where they intersect with the Rayleigh coefficients here, we get 0.01 Lyra's damping. So we also have the yellow line. Now, the yellow line is where I have set beta equal to 0, but my alpha coefficient is still considered. Well, the whole point of this is that mass and stiffness damping considerations affect the overall damping ratio. There's two components. That's the mass and the stiffness. Well, when we set beta equal to 0 for this yellow line, we're only considering the mass proportional damping effect. This blue line is where I've set alpha equal to 0, but I've kept my beta coefficient. Well, this is the stiffness proportional damping effect. Now, when we consider both alpha and beta, well, this is a combined mass and stiffness damping considerations. One other thing I wanted to mention, so for our particular structure today, for any angular frequencies that are within this range between our dominant modes, well, the structure would technically be considered underdamped. And for any angular frequencies outside of this range, more so in this area up here or slightly over here, that's going to be where our structure is considered overdamped. So just interesting to see Rayleigh coefficients and Rayleigh damping considerations plotted here for our structure. Okay, so jumping back to RFEM then, remember we solved for alpha and beta here, so we want to type in those values now at 10246, and beta is equal to 0006211. And now we're ready to run our calculation. So I click OK and calculate, and for the sake of time, I'm just going to jump to an already saved model here. It doesn't really take that long, but we'll just go ahead and jump to this already saved model, and immediately we're brought back into RFEM. And we're still within the RF-DYNAM Pro module, but we're just viewing our results graphically. Now in our dropdown, we have our natural vibration case, but we also have our dynamic load case for linear time history that we've solved for here. We do have some tables available, but I think the most important element in taking a look at really what's going on with our structure and the results is something called the time course monitor. So with our time course monitor, we have this drop down over here. I can view my members, my nodes, or support nodes. What I'd like to do is to choose nodes, and I'm going to zoom in to a node at the front of my structure here. I just click it graphically, the program automatically updates, and now I'm viewing the displacements in the X direction for this particular node, which you can see there is a red line there which indicates which node I'm looking at. Well, I can take a look at this time course monitor and immediately know I have a huge problem. This is what resonance looks like. This is when our excitation frequency coincides with the natural frequency of our structure, and our deflections just grow bigger and bigger and bigger. And eventually we're looking at a deflection here of 3 inches at the end of our 10 seconds. So inevitably our structure is going to fail. We can see this apparent in any one of the other values here that we can use in our dropdown. For example, we can view different accelerations, velocities. We can take a look at acceleration in the X direction for this node as well. Again, resonance is very apparent here. So not only that, but remember we had these tension-only members for our lateral bracing in the back. Well, let's take a look at what the normal forces for this tension-only member looks like. So I click on the member graphically, and then I want to take a look at the normal forces within the member. And again, we obviously have resonance. We've already determined that, but this is a tension-only member. I certainly have tension forces here, but I also have compression forces. Well, this is a cable element. By no means can it take these compression forces, but this is a limitation of a linear analysis. That tension-only member was replaced with a truss member that can take both tension and compression. So the question is, well, how could my structure possibly look different in terms of my natural vibrations if I were to account for the failure of these tension-only members? So we want to move on to a second natural vibration analysis study where we deactivate these failed tension members. So what I'm going to do is I'm going to jump back to my natural vibration case, which we can easily do that with our drop-down box here. And let's go back to mode shape number 6. Remember, this is our dominant mode shape in the X direction. Well, I think it's pretty apparent here that we can agree on which members are failing when our dominant mode looks like this. If we take a look at member number 1 and member number 4, these are the 2 tension-only members that are in compression for this dominant mode shape in the X direction. So what I'd like to do is to completely deactivate them and to rerun my natural vibration analysis. So how can I do that? Well, back in RFEM, I'm going to create a new load case. Now, remember, load cases are something that I apply my dead loads to, or I applied my centrifugal forces to. Well, for this 5th load case, I'm going to call this one tension only deactivation. And I'm not going to count for self-weight. I'm not going to apply any loads whatsoever to this load case. What I want to do is under the calculation parameters, we have a few extra features here, one of them being deactivate. So I now have a deactivate tab available, and I can graphically select those 2 failing tension-only members for this dominant mode shape. So members number 1 and 4. I'm going to completely deactivate them for this load case. That's all I want to do. So what I'm going to do now is going to go back to the dynamic module. I can just double click on it over here in my project navigator. jumping back to my natural vibration case tab, I'm going to make a copy of what we've already previously done. We already created natural vibration case 1. I'm going to create natural vibration case 2 as a copy and rename it to deactivation. Everything remains the same from my first case, the acting mass combination, the mass matrix, but remember I said that we're going to get back to the stiffness modifications. Well, this is where we can account for the failing tension-only members, and we can import the deactivated members from load case number 5, tension-only deactivation. Now, it's important that you don't add additional loads to this load case, and the reason why is that the geometric stiffness matrix will be imported in from RFEM and can significantly affect our natural vibration case in a way that we don't want it to. So rather, we left this load case empty with only those members 1 and 4 deactivated. So all we need to do now is click OK and calculate. So the program will cycle through this. We'll take a look here at our natural vibration cases for this second load case. And I immediately jump, well, let's take a look here at our drop-down. Natural vibration case 2 is now available, and I'm going to jump to the effective modal mass factors. So mode shape number 1 still remains our dominant mode shape in the Y direction. That's great. I didn't make any changes in the Y direction, so I wouldn't anticipate that that dominant mode shape would change whatsoever. But if I continue on down my table, well, now it looks like mode shape number 4 is now my new dominant mode shape in the X direction at 84%. Remember, it previously was mode shape number 6. So what we'll do from here is jump back to the natural frequencies table. And again, mode shape number 1 remains unchanged, but our new dominant mode shape number 4, has an angular frequency of 10.53. The natural frequency is 1.67 hertz, so this is less than half of the excitation frequency that we're seeing with our machines. So this tells me that, okay, well, maybe resonance actually isn't an issue. It's just the limitation that we had with these tension-only members that we had to consider them as truss members. So you might think, well, okay, let's jump back and just do another linear time history analysis, but we can't. If we were to take a look at our dynamic load case 1, linear time history, nothing's changed here. That's because those tension-only members are still being replaced by truss members. We're still going to see resonance because we don't even need a natural vibration case for this particular solver. They're not related whatsoever. So what we do need to do is to move on to a nonlinear time history analysis. So we can access our add-on module again under add-on modules, current module. And now we're going to activate nonlinear time history with a time diagram. Now, none of my tabs have changed here. The only thing that looks different under the dynamic load case is I have 2 additional solvers available here, which again, we went in great detail within the PowerPoint. I'm going to just simply make a copy of my linear time history, and all that I need to do here is to rename it nonlinear time history and to change the solver type. So for today, we'll utilize the nonlinear implicit Newmark analysis. So the time history analysis here can all be left the same. Now there are maybe the possibility you want to decrease your time steps for calculation, especially with a nonlinear analysis now. So that's something to keep in consideration. For today, I'm going to keep it as 0.001, making the assumption that our structure doesn't change much even if we go to a smaller time step. Calculation parameters, everything is left the same here as our linear time history, even damping considerations. Now, realistically, remember that our dominant mode shapes have changed. So we probably want to go back and to reconvert our Lear's damping to our Rayleigh damping coefficients, alpha and beta. Now for this example today, it really doesn't impact our structure too much, so I just left the alpha and beta the same. Then we're simply ready to run OK and calculate. Now again, for the sake of time, I'm going to jump to an already saved model where I've reran the nonlinear time history. And now we can see our results available in RFEM. Under my dropdown, I have natural vibration case 1, natural vibration case 2, linear time history, nonlinear time history. So all of the previous information that I've done with all the other cases are still available here, but now we're just focusing on the nonlinear time history. Now, as I mentioned before, the time course monitor is most important to take a look at the response of our structure. So let's take a look at the drop down here, the nodes, and let's zoom into that exact same node that we were looking at before. And we're looking at displacements in the x direction. Now we've made no changes to the structure. All that we're now considering is the nonlinear elements that were defined within RFEM, and you can see that our time course monitor looks much, much different. We no longer have resonance. In fact, we only have a max deflection here of 0.273 inches at just a short period of time over this 10 seconds. We can also take a look at accelerations, accelerations in the x direction, for example. Maybe we want to take a look at accelerations in the z direction. So accelerations are very important for us as structural engineers because this is something that we have limitations on depending on, what this structure is going to be used for. So for today, this is an industrial structure. We probably won't have too many humans occupying the structure, but if you're designing a hotel or an office where people are sitting or sleeping or whatever else all day long, accelerations that are extremely high can be very unpleasant, intolerable, and it's something that a lot of codes really place limitations on, and they set this usually at less than 10% of G. Now, depending on your structure, though, we might need to set that much, much less than this. For today, looking at vertical acceleration in the global Z direction, we can take a look at the root mean square value up to 10 seconds. We get the average value here of around 6 feet per second squared, which I'd say is okay. Now, also for industrial structures, though, for accelerations, deflections, velocities, anything of the sort, you might want to limit it because these machines that are sitting on these structures are very sensitive to this type of movement. So that's how we can view all of this information through the time course monitor. Now let's jump back to our tension only member. So I'm going to graphically select it here, and I'm going to view in my drop down my normal forces for this member. Well, this looks significantly different as well. You can see here for my tension only member, only tension forces are available. The minute that I have a compression force within this member, it completely fails. But then compression forces, it fails. Once tension is reintroduced into the member element will be brought back into the time history analysis, and that will continue on for the full 10 seconds. So that really summarizes how something like a nonlinearity within RFEM can be accounted for. I have another quick little example today to showcase other nonlinearities that can be considered with a nonlinear time history. And what I'd like to do is to consider nonlinearity within my supports here. So what I want to do is to take this front center support, and I'm going to double click on it to create a new support type. Now currently this is just a typical pin type application. You can see here we have our 6 degrees of freedom, 3 in translation, 3 in rotation. Now for my new support that I'm going to create, I'm going to introduce a nonlinearity, and that nonlinearity is going to be failure all if positive PZ. Well, Z is my vertical deflection. So if I have any uplift at this support, I want this entire support to fail. Well, this is a nonlinearity. So I click OK because of this new definition type. I clear my results. I take a look at my model back in RFEM. You'll notice that the rest of the supports are green. This one is now blue. That's the program just indicating that I've applied some type of nonlinearity to this support condition, which is nice to be able to differentiate it. Now, under the dynamic analysis module, jumping back to dynamic load case here, I'm going to utilize the same nonlinear time history. Again, we can use the same solvers. We're using the same structure. I just have changed around the support condition a little bit. What I do want to do under the time history analysis, though, instead of 10 seconds for my total time, I only want to consider the first 2 seconds. We'll take a look at only the first 2 seconds for our results. So once this is done, I can click OK and calculate it. Now, the one thing to check before we run our calculation, though, remember that I have the linear time history that I'm also solving for. Well, this is really just going to bog down my solution time. What's nice is that we have this feature here where we can uncheck to solve. So all of my information is still there. I just don't have to go through the solution time if I'm really not interested in those results, but I can easily activate them again to resolve it. Now, again, the natural vibration case, same scenario. We do not need a natural vibration case for the nonlinear time history. So if I'm really not interested in the natural frequencies and mode shapes of my structure, we can always deactivate the to solve function here, and you can also right click and set not to solve. So now we click OK and calculate, and we're only going to cycle through our nonlinear time history. So again, I have this saved as an additional model here. This is eventually what the program would present to us back in RFEM. We have our dynamic tables here for nonlinear time history. Now, this support condition looks a little bit different than what we previously saw. So once again, utilizing our time course monitor, I think this is the best way in understanding what's going on with the structure. Let's take a look at our third option here called support nodes. So now we only have 6 support nodes available. I'm going to take a look at support node number 8. I have my big red arrow showing me exactly where that is within the model. And I'm going to look at the support forces in the vertical direction. Well, here is where you can see that we have no uplift forces. So that nonlinearity was completely accounted for with the nonlinear analysis. So at the beginning of the solution, the support condition here has failed. We have uplift, but then at about time 0.027, it looks like we have some type of downward force, so that support is reactivated. Then it fails again. And then at about time 0.354, well, it's activated again for a short period of time. And then for the duration of the 2 seconds, it's completely failed, most likely because we have uplift forces here. The other way to kind of tell what's going on is to take a look at our vertical deflection at the bottom of our column. So what we can do here is to set this to member. I can graphically choose this member here. And I'm going to look at displacements in the Z direction. And we can see that at this beginning of time, well, this is where my support is activated. So I have no displacements in the vertical direction, but then my support fails and I have vertical deflection. Well, for a brief moment in time, the support is activated again. And then for the rest of the 2-second duration, well, the support has completely failed. So what's also really beneficial with this time course monitor, and this is true for the linear analysis, nonlinear analysis, and any one of these options available within the results, we can view a nice little video here. Now, once I take a look at this video, what it's going to do is it's going to cycle through this time course monitor here, show me exactly where I am. Well, if we can even zoom in here and see the moment where our support condition completely fails. Now, as we cycle through this, well, there is a certain period of time coming up where that support is reactivated again, and we don't have any deflection. Well, and then it fails again with uplift. So now our column is off floating somewhere. Now, any one of these animations can be saved and exported out onto your computer, which is nice for calculations and to submit along with your calculation package. So that is just another example today of how a nonlinearity can be considered for our time history analysis. Jumping back to the PowerPoint here, that concludes our webinar today. So I know that was an incredible amount of information over the last hour. You can always visit our website at dlubal.com to learn more about these dynamic modules or more about RFEM or maybe some of the other features that we offer. We do have many social media sites as well. So between our website and these social media sites is access to videos, newsletters, events and conferences, technical articles. Again, I mentioned our YouTube channel, which has all of these webinars that are previously recorded posted there for anyone to view. Our email at our Philadelphia office is info-us@dlubal.com. So if you do have any questions or comments about today's presentation or anything else, feel free to send us an email or you can give us a call. The number again here in Philadelphia is 267-702-2815. Now, we will have many more upcoming webinars. I try and do them approximately every month to 2 months. You can register at dlubal.com under support and learning webinars. As most of you know from today, I do send out a couple reminder emails when those are going to occur as well. So many of you would like PDH credit for today. That's great. I'm happy to issue you a certificate for that PDH. Just a couple requirements. Number one is I just ask that you were here for the full 60 minutes. And number two, that you request your PDH for you and anyone else that was in attendance, and send us an email to info-us, that's info-us at Dlubal, dlubal.com. So again, send that request to info-us at dlubal.com, and I'll send you an email back with that certificate. And with that said, that concludes today's webinar. So I want to thank everyone for attending today. And as always, we hope to see you at the next one. Thank you.